Well, we're going to look at the third lecture for Chapter 7. So this will conclude our study of Chapter 7. And this particular lecture is focused on Uranus and Neptune, the other two Jovian planets. Here's two nice pictures of Uranus. Uranus was named for the first Roman god of the universe, the father of Kronos, or Saturn. So here's the first father of the universe, and Saturn coming next, and then Jupiter. After that, Zeus in the Greek mythology. It's the first planet discovered since ancient times. And these two nice pictures on the left is a picture taken by Voyager 2 in 1986. On the right is a picture taken by the Keck Observatory, very recent picture, and you can see that that the appearance of Uranus has changed since more than 20 years ago. And this is not due to a photographic problem, because the resolution of Voyager was very good. Voyager was right there at the planet. So that indeed is how Uranus looked in 1986. It has more to do with the changing appearance of Uranus since that time. William Herschel discovered Uranus in 1781, and here's a picture of him actually discovering the planet Uranus, or at least a depiction. If we look at the planet, we find that its diameter is just about 4 times the diameter of the Earth. And its mass is 15 times greater than the Earth's mass, yet its density is much less than the Earth. The Voyager picture showed no features, just a green bluish disk in 1986 with no particular bands or storm features on the surface. Here's a comparison of Uranus again to the Earth and to the Earth's moon, and we can see how much that we are dwarfed by this planet. Here's also one of Uranus's moons, Ariel, and the shadow of that moon on the surface of Uranus. So very nice picture, recent picture. Uranus's rotation is well known. Uranus is tipped over, and we can observe a spot moving along its equator here. Here's how it looks 3 hours later. It has moved that much angle in 3 hours, and with a little calculation you can find out that the equator rotates slower than the upper latitudes, and the rotation period is 17 hours and retrograde. So Uranus is rotating retrograde 17 hours for one full rotation, which is faster than the Earth, but slower than Saturn and Jupiter. And also the equator is slower than the poles, which is the opposite of what we found for Saturn and Jupiter. Uranus's axis is tilted by 98 degrees, and so 98 degrees tilted the axis. It's tipped over on its side, possibly from some ancient collision. Not this collision, but some ancient collision from some other large object. So it's tilted over 98 degrees, almost 90 degrees. And hence, in its 84 years that it takes to go around the sun, the pole will spend half that time faced towards the sun, and then the other half faced away from the sun. So there will be 42 years at the pole, 42 years of constant daylight, and then 42 years of constant darkness. And in 1986, when Voyager saw Uranus, Uranus's pole was pointed towards the sun. So Voyager was seeing a Uranus that was being uniformly heated on that side, and hence there was no diversity, there was no differential heating causing bands or storms to appear. So hence it looked like just a pale green, solid colored disk. Now 21 years later, in 2007, we have this orientation where now the equator of Uranus is facing towards the sun. Uranus is spinning with the sun hitting it as it's spinning, and hence it has differential heating, and this gives rise to the band structure that is observed now on Uranus. Here's how it looked in 1986 from Voyager 2. Incidentally, Uranus emits as much heat as it gets from the sun, so there's no internal heat source for the planet. It's the only Jovian that does that, where it's just emitting just as much as it gets. Here's a progression, though, in recent years. From 2001 to 2007, we see as Uranus is getting more and more edge on, and finally in 2007 is perfectly edge on, spinning like this in relation to us and the sun. Hence, a more recent picture shows much more clarity of distinction of bands and storms on the surface of Uranus. Very beautiful picture here, showing very colorful bands along its surface and the ring system. All the Jovians have rings. The ring system of Uranus and its moons. The outer atmosphere of Uranus is comprised of hydrogen, 84%, helium, 14%, and methane, 2%. Uranus's atmosphere lacks the ammonia of Saturn or Jupiter, so it doesn't have the ammonia hydrosulfide, the brown bands. The methane absorbs red light easily, leaving a bluish-green color. So the general hue of Uranus, and as we will see for Neptune, is that it has this bluish-green color due to the fact that it has enough methane in its atmosphere to absorb red, give off blue-green. Here's a look at Uranus with its equator almost 9 degrees tilted, and these moons going around the equator. And here we can identify those moons. Uranus has no large moons. It has 6 medium-sized moons, but no what we might call large moons in comparison to the large moons of Jupiter, Saturn, and our large moon. More on the moons later in another discussion. Here's a recent picture taken by the Hubble in 2006, and we identify originally 11 rings around Uranus, but the Hubble in 2006 found 2 more with this high-resolution photograph. As we see, we can identify these 11 rings originally and 2 more, plus 2 more new moons. So Uranus is adding moons as well. At least they were there, but we're just identifying new moons. If we were to look into the interior of Uranus, we would believe that there somewhere would be a large rocky core immediately surrounded by liquid hydrogen to be cold enough, and then a mantle comprised of ammonia and water. So you have an icy water ammonia slush as the mantle of Uranus, water being a key component of that before you get to the atmosphere, which is comprised mainly of hydrogen and helium. Here's a look at our solar system. Pluto is on this look, but Pluto's now a dwarf planet. But we have Uranus, about 19.2 astronomical units away from the Sun. And we have Neptune, which is another 10 astronomical units away. Uranus takes 84 years to go around the Sun. So if you saw it in one particular month in 1 year, then you might expect to see it in that same month the next year. Because if it takes 84 years to go around the Sun, and we go around it once, then Uranus will only move about 4 days in the calendar from year to year. Neptune has a distance of 30.1 astronomical units, so Neptune is about as far away from Uranus as Uranus is from Saturn. Another 10 astronomical units, 10 times our distance from the Sun, further away from Uranus. Neptune revolves around the Sun in 165 Earth years, almost twice as long as Uranus. So definitely, if you see Neptune in the sky 1 year, you probably can wait for that same month within a couple of days and see Neptune in that same sky. It's not going to move much from year to year. Uranus will take a lifetime to go around the Sun. Neptune will take 2 lifetimes. Here's a picture of Uranus and some moons, and you can even see somewhat edge on the ring system in this picture. And this is a very nice picture because it's also showing Neptune in the background. So this is just a telescopic picture from the Earth, but it's kind of neat where you got Uranus and Neptune in the same picture. Well, two astronomers, Adams and Leverrier, independently discovered that Uranus was perturbed by the presence of Neptune. In other words, Neptune being in its space, Uranus didn't like that. So it definitely was perturbed that some other planet would venture into the outer solar system, so it was not the last planet in the solar system. Now, Uranus was perturbed in a different sense, as perturbed by the gravity of Neptune, which pulled it a little bit off course, and hence these two astronomers were able to predict that Neptune existed. Leverrier and Adams. So they independently predicted the location of Neptune based on the perturbation of the gravity of Uranus. Uranus is being pulled off course. And so they predicted this position. Another astronomer, Johann Galle, looked to that position and discovered Neptune. So the three of them get credit. However, they might have fought over who should really get credit. And so, since Neptune perturbed Uranus, eventually Adams and Leverrier were perturbed at each other and wouldn't talk to each other anymore. No, not really. Just made that up. Here's Neptune. Named for the Roman god of the sea. Neptune, Poseidon is the Greek god of the sea. Neptune is the Roman version of Poseidon with his Triton stick. Neptune cannot be seen with the naked eye, but is visible through binoculars or a telescope, and we can see in this picture taken by Voyager 2 that it has images in 1989, so 3 years after it had taken images of Uranus, and revealed dark atmospheric bands and spots, reminiscent of the other Jovian planets, especially Jupiter and Saturn. At that time, not reminiscent of Uranus, but now we see that Uranus has the same, looks very similar to the way Neptune does in these pictures. Neptune also is about the same size as Uranus, about 4 times the diameter of the Earth, 3.9 times greater than the Earth. Its mass is 17 times greater than the Earth, so it's a little bit more denser than Uranus. There really is truly a sister planet to Uranus, though, in terms of relative size and density. Density is greater than the other Jovian planets, but much less than the terrestrial planets. Neptune undergoes differential rotation, which means that not all of its atmosphere rotates at the same rate. In fact, again, like Uranus, its equator rotates slower than its poles, just the opposite of Jupiter and Saturn. The rotation period is 17.5 hours, which is similar to Uranus's rotation period, which was 17 hours. It has the axis tilted at 29 degrees, which allows it to have this band structure because we're getting more of a uniform heating as the planet turns in relation to the Sun. Here's a look at Neptune. You can see some cloud-like structures here and the great dark spot. Compared to Uranus, the outer atmosphere is similar, but atmospheric features are more visible, at least than the earlier picture of Uranus by Voyager. Now they both look kind of similar. Neptune is a lot more bluish, a lot more green-bluish, because it has a larger percentage of methane, 3% as opposed to 2%, which in relation is 50% more methane, giving it more absorption of red and more of a bluish color, which is appropriate for the Poseidon or Neptune, god of the sea, which reigns over a blue ocean. Wind zonal flow patterns and highly visible storm system, the great dark spot in these pictures. But the dark spot had disappeared in 1995 when the Hubble took pictures of Neptune. Here's the Hubble pictures, and the dark spot is gone. Here's a closer look at the dark spot taken by Voyager. You can see some cloud patterns as well. There's a cyclic storm. Here's some very nice upper clouds in the atmosphere of Neptune. So definitely some nice atmospheric features going on there. Here's Neptune and its largest moon, Triton. Neptune has 11 known moons. Largest moon, Triton. Triton's over here, this little dot over here. We can identify it. Let's point to it. There's Triton. That little moon up in the corner there. If we were to look into the interior of Triton, we would see something very similar to the interior of Uranus. Mainly a rocky core in the center, surrounded by liquid hydrogen, and then a mantle comprised of water and ammonia, a slush of water and ammonia slush, and then an atmosphere of mainly hydrogen and helium, 84% or so hydrogen, helium 14%. Very similar to the interior and atmosphere of Uranus. Here's a comparison of Uranus and Neptune's magnetic field. Uranus is tipped over 98 degrees on its side. It's turning that way, but its magnetic field axis is up 60% in the opposite direction from its rotation axis, And Neptune's field axis 46% off from its rotation axis. So theoretically, they're not conforming to the dynamo theory. The idea is that if there is metallic and substance inside and it's spinning with the rotation axis, then the magnetic field should come out near that rotation axis. That's the dynamo theory. But neither one is conforming to that, at least according to measurements taken by Voyager. I have a theory that maybe the Voyager measurements were wrong, because this dynamo theory is a pretty good theory, and it's explained a lot of the effects of Saturn and Jupiter. And maybe, as you can see, both these measurements to the orbital plane were the same for Uranus and Neptune. So maybe somehow the measurement on the Voyager 2 spacecraft, there was equipment failure there and didn't quite get a good measurement on the axis of the magnetic field. But that's just my own theory. But if that's incorrect, then this is a very nice puzzle that needs to be solved. Each magnetic field of Uranus and Neptune is 1/10 as strong as Saturn's, but still 100 times stronger than Earth. So it's still, both of them still have significant magnitudes of magnetic fields, 100 times stronger than ours. Neptune emits 2.7 times more energy than it receives from the Sun. Saturn emits 3 times more. So Neptune emits almost as much energy in terms of its proportion to what it receives as Saturn does. The energy source for this is unknown, but we can see that there is definitely some kind of cloud weather patterns going on. So maybe there is some kind of rain going on and condensation going on in Neptune, creating this heat source. But there's not enough known. Neptune's too far away, and hasn't been enough study to figure out what is the source of this energy. That concludes the study of Uranus and Neptune, this third lecture on Chapter 7. And now you should be ready for the questions on this chapter.